Welcome to the Autobach Experts on Demand education series. This is a previously recorded webinar presented by Dr. Jerry Stark titled CCAFO and CA7, Elevate Your Patients with Dynamic Energy Returning AFOs. In this course, Jerry will cover the empirical evidence, pathomechanics, clinical assessment, componentry options, evaluation, and implementation of this dynamic orthotic design option. This course is approved by ABC for 1.25 CEU credits. Please note that in order to receive credit, you are required to take the quiz and pass with a minimum score of 80%. The quiz link can be found on our Experts on Demand webpage or in the YouTube video description below. Enjoy the webinar.
I hope I'm not too loud, and I hope you can see the screen. Does everyone see it? Yeah? I didn't really necessarily like this initial slide, so I kind of doctored it up for the rest of you. I think that looks nice. I'd like to introduce Jose Matthew. She's with us as well. Unfortunately, my new body actually blocks her here, so we're moving on. So thank you so much for your time. I see there's so many of you here with us today, and really appreciate that we're going to talk about ankle foot orthoses, more specifically the designs we have from Autobach, the Carbon Ankle 7, and the custom carbon AFO. Sometimes we refer to them as the CA7 and CCAFO, and you can too if you want to sound really cool. I'd like to thank Ted Friedman, Ron Wilkinson, Kurt Kowalczyk, and Jose for helping with this lecture today. So as always, we begin every lecture with Autobach with our mission statement, which is to help people maintain or regain their freedom of movement. And I got to say that's really appropriate for orthotics, especially because it's really difficult. You know, orthotics is more difficult in some ways than prosthetics because we have to understand the pathomechanics of what the patient is presenting, compare them with the natural human locomotion principles that we know, and try to accentuate and attenuate any sort of deformity, but also allow for mobility. So you orthotists out there, you got a tough job. So the learning objectives obviously are to look at gait terminology and understand it a little bit better, but also look at double support and what it means, not only in terms of mobility, but also protecting the patient and maintaining their mobility throughout life, but also not just at the ankle, but the knee and the hip as well. So we're going to look at the muscle activity and joint motion. And then we're also going to look at Carbon Ankle 7 as it relates to how you successfully implement this for those gait patterns, and then the custom carbon AFO. Along the way, we're going to learn a few things about rollover shape and maybe pendulum gait, and also how carbon affects the guidance of orthotic design. And here's another thing about orthotic design. It's changed over the years, right? Originally, orthotic design was really meant to stop the deformity, lock the patient up. So rather than locking and popping like we are with like Rerun from Good Times or Give Me a Break, what we're trying to do is we're trying to, that's what's happening. The thing is we're trying to provide guidance. So it's not about just stopping the gait and limiting it and locking it. It's about guiding that, not just in the sagittal plane, but in the frontal plane and transverse plane. So we have this nice little graph that kind of shows the relationships between what we have in terms of, orthotic design and polypropylene or copolymer. And then we have ground reaction AFO and double action AFO where we can adjust that. But really we're stopping gait at a certain point. It is adjustable, but it's not necessarily responding to the dynamic movement. We also have off-the-shelf devices. We certainly have ours called Walk-On, the Walk-On Reaction and Reaction Plus, which can also provide an amount of control to that tibial progression. It also provides that rollover shape, but they're also limited in that they're made for certain set sizes. So when we talk about coupling with the patient, that's really important because this coupling or interface with the patient can provide it in a custom way with the CCAFO and the Carbon Ankle 7. So it's important to review the different terminology. Of course, the eccentric contraction is a lengthening or muscle lengthening, which we typically see in most of the gait analysis that we think of, because it's really the opposite as far as the moment. So if we see a dorsiflexion moment, we're probably seeing the eccentric lengthening of the plantar flexors and vice versa. And then Concentric contraction, we see a few times in gait, obviously, when the hamstrings are shortening during an early swing, an isometric contraction where that really it's just holding in place, such as the gastrocnemius and the triceps surae, and then the isotonic contraction. This was of course, the isotonic contraction is really what Arnold Schwarzenegger credits with his massive bulk, because the thing is that he held it to an overload situation and then it pulled him down. So this is really important, the isotonic contraction. So when we look at the phases of gait, we've seen this a number of times before. You that are orthotists have seen this in almost every lecture, and yet it's good to remind ourselves of it. 60% is actually in stance phase and 40% in swing phase. But every time I look at this, I always get something new out of gait and understanding gait. The important thing is I think we sometimes look at the 20% that's in double support, and this is really important, as well as understanding most of this control during gait is, of course, eccentrically relaxing and allowing a certain controlled fall. Cadence or cadaver are related in that it's the act of falling. So when we're talking about gait, it's really this controlled fall, and very little energy is being put into the system in terms of evolution. We were made to walk quite a bit in our lifetime. So when we look at this review of initial contact and heel strike, initial contact really is the main objectives are initiating the heel rocker and really providing for that impact deceleration. So we're making contact with the floor. There's 30 degrees of flexion of the hip and full extension of the knee. The ankle, sometimes we look at these snapshots that belies the actual dynamic nature of gait. The ankle's moving from a neutral position into plantar flexion, and the knee flexion at 5 degrees begins to increase slightly to go to foot flat or actually shock absorption. And this extension of the knee is caused by the contraction of the quadriceps. So the quadriceps pull the leg forward and initiate heel strike. As we go into loading response, or what we might call foot flat, the body absorbs the impact of this foot, and the hip slowly moves into extension. The knee moves into natural 15 to 20 degrees of knee flexion. This provides the shock absorption. The quadriceps are eccentrically lengthening, and the ankle plantar flexion increases to 10 to 15 degrees. The anterior tibialis fires to eccentrically control the plantar flexion. And so we're really trying to provide this absorption of that impulse shock through the whole body. So while this is happening, the anterior gluteus might appear to be eccentrically lengthening, but it's moving the hip joint into the internal rotation and stabilizing the system or the upper body for weight acceptance. Then as we move into late mid stance, the hip moves from 10 degrees of flexion and extension it's extending by contraction of the gluteus muscle, but also stabilizing the knee. And so then the ankle becomes supinated and dorsiflexed. And so the supination force is augmented by the activity of the ankle plantar flexors, which act to essentially control the closed chain dorsiflexion and also provide a stop. So in pathomechanics, this sometimes has been impeded. So the patient needs to look to other types of intrinsic or extrinsic ways of controlling this. Then we move into terminal stance, and this is where the action happens. And it's important to look with all of these phases of gait. What's the trailing leg doing? You see? So when we look at terminal stance, the opposite contralateral limb is beginning to reach the end of swing and go into heel strike. So it's important for the terminal stance. The toes are actually being loaded, and it's providing a platform to initiate the swing phase. So here we can see that there's about 10 to 13 degrees of hip extension, and then it goes into flexion during swing. And so what we're looking at is being able to prolong that load bearing. Now, this is what's so essential, either we're talking prosthetics or orthotics. What we talk about is a thing called effective foot length, carrying the support all the way to the toes. I'm reminded some years ago when I was watching someone walking, she was walking in her sandals, and I noticed that the toes abducted in the sandals. And what this does is provide a late stance platform for the limb to move forward into into swing phase, you wouldn't see that necessarily if somebody were wearing shoes. So then we move into initial swing. Initial swing begins to happen. The limb derotates because we're in an open chain rather than closed chain. And so we're beginning the swing phase through mid-swing to terminal swing and eventual acceptance of the load. So this is a pretty interesting graph or chart. And once you get past just that it looks really amazing, maybe the guy's legs are a little bit apart there. I don't know if he's looking for a place in the woods, but if you look at the triceps surae, look at the far left, look at the triceps surae and how it fires up. Now, I want you to imagine if the triceps surae were not as active or delayed, what types of muscles would have to be active to help that along? Certainly, you would look at something like the gluteus maximus would have to maintain its contraction to help that along, or maybe in terms of time, the patient would unweight that lower limb so they could advance. So this is really what we're talking in terms of custom carbon AFO or carbon ankle 7, is how can we help that triceps surae if it's weakened or lowered in terms of muscular activity, how could we enhance that so the gluteus maximus doesn't have to work as hard and we can delay the amount of time, or not delay, but we can prolong the amount of time spent in single leg support so we can actually protect the other limb. That's an important part of what we do as prosthetists and orthotists. We're not only providing greater mobility for the limb we're dealing with, we're actually providing protection for the contralateral limb as it goes into heel strike. So during the gait cycle, it's always important to remember that, we're basically dealing with eccentric contraction or lengthening. Now, why do we mention this so often? I know that you all know what eccentric contraction is. The thing is, it's a much more dynamic slowing of that moment, right? So it's not necessarily coming to a mechanical stop and locking up. And that's why, I think orthotics has changed so much. It's not about stopping and locking and popping. It's about actually locking or allowing certain dynamic motion and allowing it to occur in a very physiologic way. So this emulates, in a sense, when we use carbon, when we use other types of components, this allows it to emulate this eccentric contraction. So the muscles are usually active in opposition to the moment. So when we learn about the different types of moments in gait at the ankle, when you look at dorsiflexion moment, that's when the plantar flexors are eccentrically lengthening. And you can see how important those plantar flexors are in gait. Now, the thing is, and it's important to remember, there are actually two human walking theories. One is the one that we're primarily used to, the 6 determinants of gait. And of course, Jacqueline Perry influenced the more modern dynamic 3-rocker system. And really what the 6 determinants of gait, we're talking about the minimization of energy costs by reducing the translation of the center of mass, both in the sagittal, coronal, and transverse planes. But there's actually another one that was a little bit later than 1954 with Vern Inman. And this one talks about in 1963, the inverted pendulum, saying that stance leg perhaps behaves more like a pendulum. And not only is this oscillation of the hip joint or center of gravity necessary, but they're actually going to be encouraging it. So this actually helps encourage movement. And so we see evidence of this and other things. We see evidence of this here in a recent measurement. You look at the center of gravity motion should be timed with when knee flexion and pelvic obliquity is happening, but it ends up it's not quite matched up. So there's a thought that maybe this is an inverted pendulum. And this inverted pendulum can be really related to a thing called rollover shape, which we'll talk about slightly a little bit later. But this idea of this inverted pendulum rocking with the center of rotation at the floor, rocking forward, is important in terms of how the patient walks. So we can see this in certain walking robots. Can you see this okay? Dean, can this be seen all right?
Yes, Jerry, it's good.
Yeah, so this is from the Delft University. You could see how with a very little amount of pneumatic control, the patient can walk, and you can see the use of the arms to actually bring the moment forward. We can also see another example of this in other types of robots, the University of Manitoba robot. They just need a 4-degree incline. It's a 3-legged robot. And then Nagoya, this robot walked for actually 33 minutes. Could you see all the motors? Of course you don't. There aren't any. It's really showing how very little is necessary, and actually very little push-off is present. In fact, none. The only thing provided in terms of potential energy is the ramp. Tim Gear in the 70s talked a lot about this. My apologies for the noise, but this is from 1978. And then finally the run bot from Goodingen. I call him the fun bot because he's just fun. Look at that guy. He's just running off like crazy. I have to get to the end here and he'll take a spill. That's the fun part. Let's see, here he goes. All right, so what's the lesson of all that? Well, I could just stay looking at robots all day long. The thing is, what it's saying is that in gait, there may be not so much a push-off, but that we want to ensure this rollover shape. So when we think about what is the difference or how are they same, I think actually both things are at play, the 6 determinants of gait as well as the inverted pendulum. So when we look at how orthotic design and component design influences this, we look at intrinsic things. So what are the components, how are they performing in terms of mechanically, what are we trying to achieve in terms of stops or more appropriately guidance, and then also in terms of alignment. Then extrinsic to the orthosis, what are the ground reaction forces, not only on level terrain, but also on uneven terrain. And then looking at, we could even look at how the patient negotiates this cognitively. And then there are intrinsic things to the user, which may be how that user negotiates that with muscle strength, maybe with their compensatory alignment. And then extrinsic to the user, we look at the ground reaction forces, and then how the center of pressure at the foot aligns with the joint axes, and how we and how we as practitioners try to manipulate that. Now, carbon ankle 7 is named because there are 7 layers of carbon that are pre-preg, very similar and to how you might design a prosthetic foot. And even though you actually see a carbon braid at the top and bottom, the thing that's the 7 layers, they're mostly unilateral layers of fiber. And that fiber is laminated together in a pre-preg, which is usually at a very high temperature, around 450, 500 degrees, about 6 to 7, maybe 8 atmospheres of pressure. And this provides a very lightweight, very flexible, very strong, very tough mechanism that can be put into an orthosis. Now, carbon ankle 7 is aligned at 7 degrees of external rotation, and that external rotation is meant to mimic the normal presentation of the limb in terms of how it progresses through the stance. Now, one thing about carbon ankle 7, you might ask, well, why 7 degrees? What makes that so magic? Well, the thing is that if you're off with that carbon, that unilateral carbon, by just 10 degrees, how much do you think that decreases the tensile stiffness of the device? Would you say it reduces it 30, 40, or 50%? And those of you might want to take a guess. And actually, you're all wrong. It's a trick question. It actually lessens it about 60%. So it's really important to match that external rotation accurately. And 7 degrees seems to capture the mid-range between how people present themselves and how they walk. So the benefits of that 7 degrees of external rotation is to really match the external rotation and support the patient throughout heel strike, all the way to heel off and pre-swing. So this allows the patient to align better with their anatomy and get the most out of their carbon return. Here you can see with just 10-degree angle difference, how much is reduced, more than 60%. So, you know, carbon is great material, but it has to be aligned so in a really particular way. So with great power comes great responsibility, and that's from Spider-Man. Someone said, no, that was from John F. Kennedy, but actually, I think that's actually from Spider-Man. So the thing is, with the great power of carbon, means that we actually have to dial in what we do as orthotists even more. We have to dial in not only what's happening in the sagittal plane, but also what's happening in transverse and frontal plane accurately. If we're off just a little bit, if we don't understand gait with great detail, that we can actually go in the wrong direction and not provide the patient what they need. So where does carbon come from? Does it come from the black sheep? Is there an ancient carbon tree based in the South Pacific? Actually, it doesn't. It's an acrylic, a polyacrylonitrile, and this is repeatedly baked down. You can see down here what happens is the thread is baked a number of times until the nitrogen double bond is cooked away, and then you're just left with a single chain of carbon. And here you can see just how small carbon is. It's about 6 microns, and that's a human hair right next to it. So you can see how small carbon is, and look at the cuticle that's on the carbon. It's very smooth, so this makes it very difficult to bond to each other. And then you can see the human hair has a certain degree of cuticle, which allows actually better bonding. Not that you would laminate with human hair, but you get the idea, right? So the thing about carbon is that we're really looking at a very sweet spot. So SM-PAN is the type of carbon that we use for most things in O&P, and this gives us the really nice tensile stiffness, strength, that allows a certain amount of bending, but not too much. Here you can see it's compared to aluminum, which actually has a fairly similar modulus of elasticity. But where you find most of this stuff, take a guess. You guessed it, Salt Lake City. That's where most of this stuff is manufactured, and that's why that has become kind of the carbon mecca of the world. So how do we know how carbon bends? Actually, if you want to know the truth, engineers don't quite know. It's so complex. You can be a Lagrangian green. You can subscribe to the von Karman model or Timoshenko. If you really want to cause an argument among composite engineers, just go in there and tell them you still use Lagrangian greens theory, and they'll say, are you kidding me? Timoshenko is the way to go. So they really argue about it. And when they argue about it, you really know they don't quite know what this exchange of potential and kinetic energy is. We really don't know. We can calculate it. We can create finite element analysis. But the only really way we can know is to make a device and test it. And here at Ottobock, that's something we do very well. We create these different layups. We test things. We test them to see what the response and stiffness will be, as well as the fatigue later on. So carbon ankle 7 is fabricated as a component of that thermoplastic. It's basically a carbon member, and then you're using it as an AFO. And you're going to use the floor reaction trim line. So what you're trying to do is lean into the anterior trim line, and then with this removable anterior shell, what you're trying to do is create this anterior loading of that lower plate. And you can get a split front area, a split front configuration with a strap closure, but the big thing is to preserve this. If it's too loose, you're not going to get that loading of that anterior foot plate. So carbon ankle 7 uses the ground reaction forces. It's utilizing it to load there. The carbon ankle 7 actually provides the response that you'd see from the triceps surae. Here in these different charts, you can see where the green are the normalized forces. The gold forces are when the carbon ankle 7 was utilized, and red when it wasn't. And you can see really when you look at that red line, it drops off, because if there's nothing supporting the plantar flexors, you can see why you'd have a problem, and you'd actually have a late stage drop off at the limb. And then it just doesn't, it tries to match that green line better. And then when we go to the knee flexion angle, this graph also shows you the start of swing phase. The red, again, is the red line is actually without the carbon ankle 7, and then the gold line is with it. And you can see how it tries to mimic this knee flexion angle better, so you don't see an excessive amount of knee flexion. So one of the things when we talk about how devices work, we can borrow certain things from prosthetics. I know this is an orthotic lecture. How do prosthetics get its way in here? But anyway, we can learn a little bit about what happens with energy return. And I hesitate to use dynamic response, energy return, but of those, I think dynamic response or effective foot length might be the key word. If we look at motion, we can actually see that like a flex foot actually flexed more than it should have. So this gray area, this is from Jacqueline Perry's seminal work. This shows you how it's actually more, it flexes more than it should have in late stance. Then if you look at moment, it actually gives you a little bit more push off than you'd actually expect. In prosthetics, sometimes with a transfemoral patient, we sometimes see this as a medial whip. But here, this is where you get what you're paying for with any sort of dynamic carbon device at the foot, whether it's orthotics or prosthetics. And this is power. Power is the rate of change in the sense of work. So what's happening is that impulse resistance is so important. See how it's in the middle range, whereas if you had something else, either a Satch wooden foot or you had a low-grade plastic foot, which mimics, in a sense, a more flaccid foot orthotically, you can see it's right almost in the middle range of power. And what this means is it's responding to loading and unweighting very similarly to the natural foot. And we can kind of see that when we look at center of pressure measurements. And orthotically, we're really limited because we're trying to enhance that. We can't just replace it like the prosthetists do. We're trying to actually simulate that response. So really what I'm thinking about is it's really about carrying the load all the way to the end of the toes. So carbon ankle 7, we could even talk about these used with stance control orthoses. This really did enhance the amount of knee extension that was achievable. So when you're talking about stance control for KFO wear, this can also have a positive effect. Of course, we've taken the carbon ankle 7, which is that main flexing member. We've tested it at all the various levels. So you go through and you look at the body weight, you look at activity level, and then you can look at the proper spring selection. We've tested all those for you here at Autobot. So when we look at who's indicated for this, well, we're really looking at soleus, paresis, or paralysis, or weakness. And so this has its effect on the third rocker during gait mechanics. So the primary function is replace or augment this absent or weakened plantar flexor group. So latent stance, we can lock things up just a little bit more dynamically, and they can load the toe a little bit more. Indications to restore that forefoot rocker, and we can use this in a prosthetic partial foot prosthesis. So we call this a prosthesis, right? That's kind of fun to say. So this prosthesis, we can restore that forefoot rocker so they can load all the way past the toes. Now, this is what's so imperative is you need to have the high anterior trim line so that you can load that anterior loading of that forefoot. It also helps mitigate the amount that the hip extensors have to stabilize the knee. Remember that graph we saw earlier with the skeleton walking? The gluteus maximus doesn't have to work as long, and you don't see, you can see it working in concert a lot better. So this is really for those types of patients where you need that third rocker. So when we look at gait pathomechanics, oftentimes we see this disrupted third rocker, and this really affects not just the ankle, but the hip and knee motion. And so we really want to decrease that, that center of gravity change and oscillation. So we're really looking at providing an additional amount of support for the soleus muscle. Here I took a little extra picture of myself. I was all swole that day. That was my leg day. I'm just kidding. But you can see we're always looking at when does the heel pop off the floor, and this is so important. So when we look at who are the ideal candidates, it's really the restoration of that third rocker. Here you can see that patient is kind of slipping their limb forward, and they're limiting the amount of time spent on their limb. So sometimes the weak quadriceps cannot initiate that amount of control. And then maybe they may even have weak hip extensors or flexors, so they can't achieve the knee and hip flexion necessary during swing. So what do you need to know? Well, you need to know the weight and activity level so we can give you the calibrated size between the 10 different sizes. This is really designed for patients with weak or absent soleus or plantar flexors. And you can incorporate in your design of the upper trim line and also for the foot and really accentuate that custom coupling effect. Because what coupling means is that it matches the shape very well, which you really can't do with off-the-shelf type orthotic devices. And this really promotes that third rocker so they can really lean into their limb and to their foot and carry that support all the way to the end of the toes. And this does promote that hip flexion during swing phase so they can have a normal step length. And then when we say energy return, I really think it's more about dynamic responsiveness. But when the weight line nears the distal end, they get the support they need for late stance. And so this can help a variety of patients. So the big thing about the Carbon Ankle 7 is to provide this progressive resistance, so this energy to return combined with effective foot length. And then this can be the part about carbon, though, is that it's imperative that you know what the patient's weight and what their activity level is, because if you don't, then we can give you the wrong size strut. And, you know, it's not a thing. My old German teacher said, Jetta, you need to know when to cheat. Well, sometimes if you cheat things, right, if you're cheating things just a little bit, something bad can happen. And unfortunately, with carbon, we don't want to have catastrophic failure, but this really begins usually with a form of crazing, right, because it begins to delaminate. Carbon's great stuff, but it has to be glued together. If you lose that matrix, then that's when you have problems. So it's really important that you get a very accurate design. So with great power comes great responsibility. You as an orthotist have to do your job even better. So you have to provide this dynamic movement. Now here's the tough part, though, and we'll talk a little bit about this. We don't quite know how much energy return you're going to get in terms of plantar flexion. So you have to kind of determine that. So for any sort of carbon member to release energy, it has to be deflected first. So how much deflection is necessary? And the thing is, it's not really adjustable. So you have to have a feel or develop an anecdotal, qualitative, phenomenological understanding of how posterior leaf spring devices work and how this particular one works. The one nice thing is that it is interchangeable. You don't have a mechanical click or metallic click with a mechanism. No lubricant or maintenance is needed, but you should watch out always for any sort of scratch or nick, because that's where a crazing occurs, where the resin begins to pull apart. But it's really optimized for, it's been tested and optimized for your particular walking speed and need. So the custom carbon AFO, this is really integrating more of the custom devices. The big thing is to make sure you do this accurately. So when you use our custom foot casting device, if you're just 10 degrees out of alignment, use 60% of that carbon fiber, and we saw that earlier. So custom carbon AFO has multiple pieces. And I really think about, you know, I've been kind of jealous of what they do prosthetically sometimes in terms of orthotics. You know, they have this nice flexible inner interface. They have this rigid or dynamically moving frame. And this is really the opportunity for you to participate in that, because you can see that you have this really flexible inner frame that's custom molded to the upper part of the calf shape and also to the foot shape. And you can achieve the amount of correction you want to have. Now you combine that with the ability to have this custom fabricated AFO pre-preg that's on the back. That's a really powerful combination. Again, this is intended for people with plantar flexor weakness, primary soleus weakness. And what is that defined by? I had a prosthetist ask me this. What is soleus weakness? Because many times prosthetists, they don't care. They don't deal with that. But it's the inability to raise the body weight on the involved side 10 times during volitional standing. The normal person can do 25. So if you want to see if you have normal soleus performance, go ahead and try that after the lecture during the quiz. Try to lift yourself just with your one leg 25 times, then you've exceeded the normal. But if it's 10 times or less, then you do have a primary soleus weakness. The other thing to look is at the triplanar instability. Sometimes we concentrate so much on the sagittal plane flexibility or stability and ability to unlock. It's also important to look at what the subtalar joint is doing. And if we can do that with a custom molded boot, we can do this a little bit better. And so sometimes this can be used in combination with drop foot, but also other types of pathologies. really, this is not intended for quadriceps weakness. You might have to do something, have something more involved for that. Yeah. So plantar flexors, sometimes referred to the triceps surae, triceps being, you know, the two bellies, muscle bellies of the gastrocnemius and the soleus. And the soleus is the one that doesn't get much attention, you know. I guess the soleus is the unsung hero. Yeah, Sheldon gets all the attention like the gastrocnemius, but soleus is like the Leonard. He makes this all happen, right? So the big thing about the soleus is it's not a two-joint muscle. So this eccentric contraction from mid-stance to initial swing is so important to be able to lock out. Now here's the question, is the foot a cantilever beam or is the foot a mechanism? Again, it's a trick question because it's both. So it's sort of like a cantilever beam, but you don't necessarily have to build up as much deflection within the physiologic limb because you have your muscles being active. So this is the type of patient you typically see. What types of gait deviations do you see? You probably see a little bit of recurvatum. We see a little bit of excessive plantar flexion, a delayed time on the limb. So when we look at normal soleus gait mechanics, we see this eccentric contraction. This really stops the advancement of the tibia over the foot. Excuse me. And we really are looking to create this heel off to extend the knee. This really acts to retain that extension of the knee and maintain it. If you don't have it, that's where the gluteus maximus has to work. And so when we have normal soleus gait mechanics, we should see this gentle oscillation of the center of gravity. So soleus deficits manifest themselves at terminal stance. We might see knee flexion. We might see dorsiflexion greater than 10 degrees, absence of the third rocker. Lack of propulsion, but I think this really is a lack of support at the toes. We see excessive hip rotation and a drop in that center of gravity. And here you can see when the patient has been treated, we've replaced that third rocker. We'd reduced that foot and ankle triplanar deformity. And now the patient can actually have amount of ground reaction force, latent stance. And the patients, you notice their shoulders a little bit higher. So we'll go backward. I want to show you this again. So look here. Excuse me. And we'll go forward again. I want you to notice how there is that lack of drop-off latent stance. I guess it's side by side, yeah. So much faster in comparison, and look at where her shoulders are, look where the center of gravity is, and look at where that knee is in a late stance. So when we think about this, this also has something to do with rollover shape. And rollover shape is when you look at the angle of the tibia in reference to the center of pressure at the floor. And if we hold the shin section stationary, we see this arc. Now this arc is kind of interesting because it's invariant to speed, load, heel height, and it's really about 30% of the leg length. We can calculate this arc. And what's interesting is the prosthetists and orthotists, we've measured this, or Andy Hansen actually did. He measured this and he found that what orthotists and prosthetists try to do is normalize this arc. Anecdotally, this is something that you see and try to emulate cosmetically. So when you look, not cosmetically, qualitatively, you're analyzing that rollover shape. So that effective physiologic foot length is around 0.83%. We see with more dynamic types of feet, it approximates that. If you have something that only has a very, only carries support to the metatarsal head, it's only about 66% of the effective foot length. So how should you choose the different spring stiffnesses? Well, they're based on, what are your patient goals? What is their height, their weight? What is the effective lever arm? And then using the activity wheel developed by Autobach, the patient can choose, you can choose with the patient what the spring stiffness should be. Of course, the clinician always reserves the right to look at the clinical needs of the patient long-term, then the patient preference for their different types of activities. So when we're ordering this, it's really custom made by Central Fab, and so we get the requirements needed to make this product. Really, the more you complete that order form, the better it comes out. And then it really helps to look at having a very optimized cast, and then optimize the reduction of the triplanar deformities and making sure you approximate where the foot is in space in terms of toe in and toe out or external or internal rotation. The estimated turnaround time is 10 days, but our fab always surprises me how fast they're getting with this sort of thing. Now, pre-preg is so important, as I mentioned. Pre-preg has a certain formula and how they lay it up, so it's really important that they get this very accurate. If they're just off just a little bit, they might miss where you want the longitudinal forces. You know, it's always nice to have some sort of backup within the literature, and this is a really great paper by Arch and Reisman, really talking about use with stroke patients, but really showed definitively how well these types of devices work, used to really look at the plantar flexion moment and the effect on late stance, late rocker. So if you have any inclination, please look up this paper, Passive Dynamic Ankle Foot Orthosis for individuals post-stroke. Again, we talk about these in terms of the continuum, right? You always have your copolymer AFO, but they're really not doing too much. And then you can make it a ground reaction if you want to, or a double action. But really that's limited by the small springs and stops that you have. You can go up the ante with some off-the-shelf type of carbon devices. But when you really need to have the late stage support, you have the carbon ankle, custom carbon AFO, and then you have the custom, you have the carbon ankle 7 that you can rely on. So those are two more devices to your armamentarium to help not just locking the patient, but allow that dynamic guidance. So I really like to thank you all for your attention. I hope it was interesting in terms of understanding what gait is, looking at also an alternative Da Vinci code type of gait, which is the inverted pendulum. And in many ways, that's some way, I think both are combined, and I think orthotists think with both of those. And then also kind of looking at borrowing some understanding what's happening with carbon. Carbon is a little bit of voodoo. We're never quite sure what's going to happen until we make it. Sort of like a box of chocolates. We're not sure what we're going to get until we make the device and put it on a patient. But as an engineer, for myself, that's very exciting. That's always what makes O&P a very exciting profession, because I never quite know what will happen. So I hope we've given you some ideas about how to guide movement. And also the main limitation is just doing your job even better to a higher degree. And we at Ottobock are here with you to help you every step of the way. Ms. Jose is with me from Canada. My colleagues Ted Friedman, Ron Wilkinson, Kurt Kowalczyk are also available to help you implement these devices. And it really comes down to knowing gait very well and knowing your patient extremely well.
Thank you for watching this previously recorded Experts on Demand webinar by Ottobock. Please click the link in the video description to access the quiz and submit for continuing education credit. If you have any questions, please contact the education team at 1-800-328-4058 or via email at us.education@ottobock.com.